Longer than most skyscrapers are tall. They are steel giants, carrying Earth's most valuable commodity. Oil tankers transport over half of the nearly 80 million barrels of oil the world consumes on a daily basis. In an oil-dependent world, no nation consumes more than the United States. But America only produces about 1/3 of its needed supply. The rest must be imported from thousands of miles away.
Regretfully, oil is found in some locations that are a great distance from markets such as the United States and in Europe. And the only way to move that is either by ship or by pipeline.
Oil tankers come in a range of sizes and are classified by their DWT, or dead weight tonnage, which is a tanker's weight when fully loaded. The 5 dominant classes are named Panamax, Aframax, Suezmax, Very Large Crude Carriers, or VLCCs, and Ultra-Large Crude Carriers, or ULCCs. The latter two are more commonly referred to as supertankers. In some cases, a tanker's classification name also specifies the region in which it can safely operate when fully loaded. For example, a Panamax is the largest tanker that can pass through the Panama Canal. A Suezmax is the maximum size tanker that is permitted to transit the Suez Canal. Larger tankers, such as supertankers, have drafts that are too deep and must use alternative waterways. Although oil tankers come in a variety of sizes, they're all built for one singular purpose: to carry oil. Lots and lots of oil. And this lone intent is reflected in the tanker's design. Beneath the steel skin of an oil tanker are a series of tanks subdivided by bulkheads. In a large-sized tanker, tanks are generally divided into 3 compartments that extend the width of the hull, and as many as 40 compartments that extend the length of the hull.
The reason for doing that is to prevent the cargo sloshing and to provide stability. I think often the easy way of explaining it is if you were to carry a large bowl of water, I think one becomes very conscious of the fact that it's difficult to maintain the stability. If you can subdivide it by putting in divisions, it makes it a much more stable cargo.
After the cargo tanks, at the stern of the ship, is a lone tower known as the superstructure, which houses all the necessary control rooms and crew accommodations. The remainder of a tanker's deck is an array of pipes used to transport oil, either into or out of the tank compartments below. As soon as an oil tanker leaves port, it becomes an entirely self-sufficient floating city, capable of producing all of its own electricity.
They have huge generating units and generate electricity to not only keep the cargo contained and heated, but also to heat the ship and to run the equipment. They're very large power plants moving across the ocean.
And the larger the tanker, the more easily it can slip through the water. Therefore, a VLCC requires only a single 30,000 horsepower diesel engine for power. The propulsion system consists of a single propeller and rudder, capable of moving a fully loaded VLCC at a speed of 15 knots. Auxiliary generators produce the ship's electricity.
Tankers, by nature, are the most energy efficient of all vehicles. In terms of energy per ton-mile of the goods transported, we're moving it at a cost of about 2 cents per gallon. So at the gas pump, the actual price we're paying for gasoline has about 2 cents for having transported the oil.
At a port in the Pacific Northwest, the Suezmax tanker British Harrier is in the process of offloading cargo to its Cherry Point refinery.
The crude we're carrying is from Argentina and it's called Escalante. We carry 1 million barrels. What's that equivalent to? Probably 35 million gallons or so. It's a lot of oil.
Although the Harrier looks safe in the calm waters of the port, offloading is actually one of the most dangerous aspects of its journey.
Certainly, this is the risky part. We change the condition of the vessel greatly. This is a dynamic process, and it requires careful monitoring to avoid incidents, accidents, bad things, really.
During cargo discharge, combustible gases are present on the deck of the ship. A single spark can lead to a catastrophic explosion. Crude oil is offloaded by huge steel pipes that extend the length of a tanker's center compartments. Additional pipes branch out from the main pipes in order to reach cargo in the starboard and port tanks. When the vessel is ready to discharge, hydraulic pumps create a vacuum inside the steel pipes, sending the cargo to more pipes that run along the ship's deck. From there, the oil is sent to a refinery or storage container via additional conduits. The discharging process for the Harrier will take 30 hours to complete.
We'll have to run our pumps carefully to get as much out as possible. And I can assure you this vessel is going to be dry as popcorn at the end of the operation.
But even after its combustible cargo has been emptied, the Harrier can still be a dangerous place.
The power of the sea is so great. You've really got to watch the weather, because if you're doing full speed and the weather does deteriorate, the combined force of the weather hitting the ship can do a lot of damage. It can take steel structures on deck just away.
To avoid accidents, sophisticated navigation tools are essential.
On this ship, you can actually program the ship to alter course itself. The navigation with GPS, and that's accurate up to 50 meters. So yeah, you just read off a dial and there you are.
Besides the weather and combustible cargo, the crew of the Harrier must battle one more hazard of sea life: boredom.
It can be boring, especially oil tankers. They're at sea for long periods. They load offshore, they don't go into port as often as container ships or bulk carriers, and they can tend to be boring.
The trip from Argentina to the west coast takes the British Harrier 21 days. To help pass the time, the Harrier is equipped with a gym, a recreation room, a bar, a full kitchen with chefs, a dining facility, and a complete complement of musical instruments.
You gotta have a love of the sea. You need an attitude, a certain attitude to do this job.
You got to love it. You got to love the job to do it, I suppose.
The British Harrier exemplifies the efficiency of the modern oil tanker. But achieving this level of efficiency took the industry over 100 years and 2 world wars. With a deadweight tonnage of more than 564,000, the Yari Viking is the world's largest oil tanker. Measuring 1,504 feet in length, she is over 250 feet longer than the Empire State Building is tall. Oil tankers will return on Modern Marvels. Today's global tanker fleet provides an essential lifeline to the industrialized nations of the world. But transferring oil by ship isn't new. Its history dates back thousands of years, when the Greeks, Romans, and Phoenicians transported oil across the Mediterranean Sea. No, not petroleum oil. Olive oil. Like petroleum oil, olive oil was the most important commodity of its day, and it commonly served as the financial backbone for an exporting nation's economy. Wood ships fitted with multiple sails were built to reach trading posts throughout the Mediterranean. Instead of transporting the oil inside the hull of the ship, the cargo was stored in baked clay amphorae. During the Middle Ages, ship trading expanded as it became cheaper and safer to traverse the world's oceans and seas. In the centuries that followed, the developments of ocean-going warships and efficient merchant carriers also led to a rapid expansion of commerce. But it was the 1859 discovery of oil, by Edwin Drake in Titusville, Pennsylvania, that would bring overseas shipping to new levels of prosperity. 2 years after striking black gold, 3 million barrels of oil were being pumped each year in Titusville, with the majority of it being refined into kerosene. Coined the new illuminant, kerosene created a demand that stretched across the Atlantic to an oil-thirsty European continent. In November of 1861, the Elizabeth Watts made the first transatlantic shipment of oil from Philadelphia to London. Storing the cargo in wooden barrels, the double-masted 224-ton wood ship carried 1,329 barrels of oil on her maiden voyage.
And those barrels had value, so having reached their destination, they were emptied and were then shipped back empty. So at the time, it was considered an efficient system, but shipping back empty barrels was not efficient.
The barrels, which each held 42 U.S. gallons, accounted for up to a fifth of the ship's actual cargo weight. In 1886, British shipbuilders improved on the inefficient barrel with what most consider to be the world's first modern oil tanker, the iron and steel constructed Glukov.
That ship utilized the hull of the vessel as the containment system. It was able to carry a larger cargo, steam-powered, wasn't so dependent on the weather, and it meant that one could actually organize the transportation on a more regular basis.
The Glukov could travel at a rate of 9 knots, holding 3,020 tons of oil in 8 storage tanks that were subdivided by a series of vertical and horizontal bulkheads. Oil was pumped into the cargo tanks from shore and was protected from leakage by boiler-riveted steel plating that also formed the outer wall of the tanks. To further maximize the amount of oil that she could carry, the ship's cumbersome engine was moved from middle to far aft. The bridge tower and officers' quarters were relocated to the middle, and the smokestack and crew's quarters placed at the stern. The bow of the ship was home to a raised forecastle that protected her against rough seas and provided storage for supplies. The Glukov's distinct 3-island structure became the standard for tanker design for more than 60 years. In the early 1900s, the world's deep-sea tanker fleet numbered 145 ships, with trading between the United States and Europe reaching 2.3 million tons of crude a year. The largest tankers in the fleet had a cargo capacity of 12,000 tons, nearly 4 times that of the Glukov. But this increase in tanker size began to compromise their seaworthiness. Sir Joseph Isherwood came up with the solution in 1906.
When the ship's going through the waves, it's moving up and down and bending in a longitudinal way. And the Isherwood system was developed to provide some longitudinal rigidity to help the vessel in terms of its bending.
Before the Isherwood design, ships were built using numerous transverse frames, which formed the ribs of the ship. In Isherwood's design, the ship's frames ran fore and aft along the length of the ship, parallel to the keel. The frames were then connected to the keel by vertical bulkheads, which also divided the tanks. By 1914, 276 ships had incorporated the Isherwood design.
The Isherwood system has been refined and modified, but it is still the underlying system that is employed in the construction of ships.
The design system for the modern oil tanker had been achieved. But the onset of the First World War would bring about a new breed of tanker for the military, called an oiler, and a new method of transferring oil, known as underway replenishment.
The tanker is a ship that's able to carry petroleum or water or some other liquid substance from point A to point B. An oiler can do that, but it also can do what the Navy calls underway replenishment, whereby it can refuel other ships while sailing across the ocean.
In World War I, The strategy of the German Navy focused on Britain's dependence on oil imports to fuel its war campaign. Germany's new weapon, the U-boat, set up a blockade in the North Atlantic to cut off Britain's oil supply. When the U.S. entered the war in 1917, the Royal Navy was limited to a 10-week supply of oil. With little time to spare, the U.S. Navy sent a fleet of destroyers to assist the embattled British fleet.
These destroyers had a very limited range. They could just barely make it across the Atlantic. To ensure that they wouldn't have any problems, the Navy arranged to have them be refueled in mid-ocean by one of the Navy's oilers.
Before the U.S. joined the war, Chester Nimitz and the officers aboard the Navy tanker Maumee designed a ship-to-ship refueling system that consisted of two 50-foot-long rubber hoses suspended by cargo booms. The Maumee was the first ship to perform underway replenishment.
The advantage of underway replenishment is that the fleet or Navy formation can keep steaming while it is refueling, as versus having to go to a port somewhere and spend the time to refuel and then proceed on to its destination.
By July 5, 1917, the Maumee had refueled 34 destroyers headed for Europe. They helped break the German U-boat blockade.
The significance of refueling these destroyers was it was the first time that anyone had refueled ships at sea in a tactical operation. And it was the forerunner of something that would happen again and again, especially in World War II.
In the mid-1930s, war clouds began to form again on the global landscape. The United States military was quick to realize that if a Second World War were to erupt, it would be a fully mechanized conflict, and tremendous amounts of oil would be needed to ensure victory.
The Navy laid out a very detailed structural plan on how the Navy was going to get from the west coast of the United States to the Far East to be able to engage its main enemy, which it felt was Japan. So it knew in the interwar years that refueling at sea would become a critical element of this.
The Navy needed a fleet oiler in a hurry and looked towards the commercial tanker industry for assistance. In 1939, the Navy purchased the 553-foot tanker Cimarron from the Standard Oil Company.
She was a very unusual ship. She was fairly large, but more importantly, she had twin screws. It's a very fast ship with a bulbous bow. They allowed the ship to have a speed of 18 knots at a time when 14 or 15 knots was the norm for a fast commercial tanker. And this speed was very important because this would allow the ship to steam with the fleet.
The Cimarron became the prototype fleet oiler for the Navy. When the U.S. entered the war after the bombing of Pearl Harbor, the Cimarron class quickly distinguished itself in the battle for the Pacific.
The real significance of the Cimarron class was that it permitted the United States to conduct the famous carrier raids that we're all familiar with. It's a little-known fact that every one of those raids was accompanied by an oiler. And this was because the destroyers all had to be refueled at sea, because they had limited range vessels.
In addition to refueling at sea, the U.S. military needed to transfer millions of gallons of oil to the thousands of tanks, trucks, and planes that would be needed in Europe and along the Pacific fronts.
Tankers were always a prime target of U-boats because they're important ships. Their cargo is important, so whenever a submarine saw a tanker, it would always go after it.
The Allied forces were faced with the challenge of building tankers faster than the Axis powers could sink them. Their answer was the T-2 tanker.
It was a standard design which allowed the ships to be built very quickly.
They actually would construct segments on shore and then bring them to the building yard, and each time they built a tanker, they learned how to build it faster or quicker.
About 525 of them were built throughout the war. They could do about 15 knots. They could carry all forms of petroleum. They were very instrumental in being able to support our forces overseas with large amounts of petroleum products.
By the end of the war, the Navy's oilers and tankers have provided an invaluable lifeline of fuel to the Allied forces. While the oil tanker of World War II had achieved new levels of performance and size, a booming post-war economy was about to give rise to the oil tanker tycoon and the dawn of the supertanker. During the invasion of Okinawa in World War II, oilers delivered over 10 million barrels of fuel oil to the fleet at sea by underway replenishment. Oil tankers will return on Modern Marvels. The end of World War II marked the beginning of unprecedented growth for the United States economy. Post-war Americans wanted to drive fast and travel far. By the early 1950s, American imports of petroleum products exceeded exports for the first time. Oil companies and ambitious entrepreneurs were eager to feed America's high demand for oil and took advantage of a unique opportunity.
After the Second World War, the U.S. government has over 600 tankers of all sorts. The American oil companies put pressure upon the U.S. government to sell off these surplus T2 tankers. So for about 4 years, the United States sells over 400 of these 600 tankers to American and foreign oil companies.
Many of the T2 tankers were retrofitted by their new owners so that they could carry more cargo. Using a process called jumboizing, the ships were cut in half, and an extra section was added to the middle, thus doubling the tanker's storage capacity. The 1950s also saw a trio of independent shipping tycoons begin to stake their claim in the burgeoning oil trade. Greek shipping magnates Aristotle Onassis and Stavros Niarchos joined American Daniel Ludwig in an unofficial competition over who could lay claim to the title of owner of the world's largest tanker.
The competition that existed between the various independent owners was just probably as much ego as it was economics of the day. There was a lot of status carrying I now have the world's largest tanker.
American ship owner Daniel Ludwig chose to go overseas to the Kure shipyards in Japan to build his tanker fleet.
That was a surprise to the industry worldwide, because historically the ships were either built in Europe or they were built in the United States. And all of a sudden Japan came in as a third competitor.
In Japan, Ludwig found a country desperate for industry and a highly skilled workforce with a proud tradition in shipbuilding. As Ludwig began to build his tanker fleet, Greek shipowner Aristotle Onassis grabbed the title of world's largest tanker owner with the launching of the Tina Onassis in 1952. His Greek rival, Stavros Niarchos, bested him in 1955 with a 47,000 deadweight ton vessel, Spiros Niarchos. But it was political instability in the Middle East that would bring tanker tonnage to unprecedented levels. The Suez Canal, which links the Mediterranean Sea with the Red Sea, provides the shortest shipping route from the oil-rich Middle East to ports in Europe and the United States. In 1956, Egypt nationalized the previously unrestricted passageway. Israel, which relied heavily on the canal for trade, considered this a threat. Joined by Britain and France, Israel declared war on Egypt. The conflict left ships scuttled along the vital waterway, and the canal was closed. Ultimately, the United Nations settled the conflict, and the canal was reopened. But the tanker industry felt it could no longer rely on the political instability of the passageway.
There was a realization that the oil that was moving from the Middle East to Europe, to the United States, had to come around South Africa, around the Cape.
The route around the Cape of Good Hope and then north to Europe or the US added as much as 11,000 miles round trip to a tanker's voyage. To maintain the normal flow of crude to both continents, tanker tonnage had to increase by nearly 100%. The industry was left with two alternatives: Either build a large fleet of small vessels or a small fleet of large vessels. The decision came down to the economics of scale.
If you had a box 10 foot by 10 foot by 10 foot, there is let's call it feet. There's 1,000 feet within that box. If you go 20, 20, and 20, it's 8 times the volume. So it's not linear. By just doubling the size, you create huge amount of volume.
And there was a rush to build a lot of large tankers, super tankers at that time. A large part of the industry said this is the future.
After the closure of the Suez Canal, Daniel Ludwig set the maritime world abuzz by breaking the 100,000 deadweight ton barrier with the launching of the Universe Apollo. The supertanker was born. Around this same time, a dramatic change began to take place in tanker design. The three-tower arrangement that originated with the Glukov was combined into one superstructure, placed at the stern, leaving the entire forward hull for tank space. As maritime engineers began to transform the tanker's design, deadweight tonnage barriers continued to fall. In 1966, the Idemitsu Maru became the first tanker to eclipse 200,000 deadweight tons, becoming the first VLCC, or Very Large Crude Carrier. Just 1 year later, the Suez Canal closed again, this time for 8 years. The industry's gamble in building supertankers had paid off. And Daniel Ludwig was ready to push the envelope of size even farther. In 1967, he unveiled the 300,000 deadweight ton Universe Ireland. Ludwig had once again established a new record in tanker tonnage. The Universe Ireland became the first ULCC, or ultra-large crude carrier. Ludwig's landmark achievements, breaking the 100 and 300,000 tonnage barriers, gave him the recognition among his peers as the father of the supertanker. But for the United States, the world's largest importer of oil, the draft of a fully loaded supertanker posed a large problem.
None of the ports could handle a ship of that draft. So what we find happening still today in the United States is these larger crude carriers come in, they stay offshore 20, 30 miles, and they actually do what we call lightering, which is take the oil from the large ship and actually put it on a smaller ship, which does have the draft to allow it to go into these ports.
Lightering typically takes place while both ships are underway. Maneuvering the smaller ship alongside the larger tanker can be dangerous.
This is a lightering fender. What we use them for is to keep the two ships that are lightering from coming in contact with each other. As you can imagine, the size of these is tremendous because there's tremendous forces involved in bringing two full-size tankers together that are carrying perhaps 300,000 tons of cargo each. We don't want them coming into contact at sea.
With the fenders in place, the ships are moored alongside each other. After checking to make sure the tankers are secured, rubber hoses measuring up to 90 feet in length are transferred over to the lightering vessel. Typically, cargo is offloaded using a 250 psi pump, which can transfer oil at a rate of 30,000 barrels an hour. By the 1970s, the growth of the tanker industry appeared limitless. But this burst of growth would soon be stunted by a series of supertanker explosions and several devastating oil spills. The supertanker brought about a golden age in the oil tanker industry. But starting in 1969, a series of accidents placed the industry under scrutiny.
In a very short period of time, there were 3 major tanker explosions. That led to immediate concern.
The entire concept of the tanker was in jeopardy, as speculation rose that tankers might be floating time bombs, capable of igniting without a moment's notice. An investigation into the accidents found that each explosion had occurred during the washing of the vessel's cargo tanks.
When you drain the cargo tanks of the oil, there's always a residual buildup on the inside of these tanks. So what we use is a high-pressure washing system. It's automatic within the tank, and when you induce oxygen through this spraying system, you've got a combustion potential. And the velocity of that spray system actually picked up static electricity. When it hit the sidewall, it created a spark, and the vapors coming off ignited. And it was tremendous tragedy.
To fix the problem, engineers designed an inert gas system, or IGS. During cargo discharge, flue gases produced by an oil tanker's boilers are sent to the IGS. The system converts the flue gas to an inert gas, distributing it to the ship's cargo tanks and displacing the oxygen. Today, inert gas systems are mandatory aboard every oil tanker in operation. After the supertanker explosions of 1969, the industry would soon endure another crisis. By the mid-1970s, world demand for oil products began to taper off. The industry, which had greatly increased its tanker fleet due to the closures of the Suez Canal, was suddenly left with a surplus of ships.
A lot of the ships that were built in the late 70s in particular went straight to layup. Several of those ships were never used, and in fact within a handful of years many of those ships were sent for demolition, for recycling, without ever having carried a cargo.
By the late 80s, the demand for oil products was again on the rise. New tankers were being built, and the industry showed signs of a full recovery. But its momentum would be short-lived, as an environmental disaster was about to change the industry forever. Since the dawn of the supertanker, hundreds of millions of gallons of oil have been spilled in oceans throughout the world. But no oil tanker spill has had a greater impact on the industry than the grounding of the Exxon Valdez in 1989. On March 24th, the single-hull Valdez hit a reef, fracturing its hull. The result was the leakage of approximately 11 million gallons of its cargo into a pristine environment.
The Exxon Valdez severely damaged the local environment around Prince William Sound in Alaska. The oil then drifted to the west and continued to damage coastline along Alaska. It killed many animals outright, from birds to seals to sea otters, and then continued to damage fish populations and other aquatic populations.
The Exxon Valdez oil spill was regretful, not only for Exxon itself, but for all the industry. But what it taught all of us is even though we were operating as safely as possible with the emergency response equipment that we thought was adequate, we learned that we needed to do even more.
After the grounding of the Valdez, public outcry and political pressure led to new legislation for tankers entering U.S. waters.
The Oil Pollution Act of 1990 effectively mandated the introduction of double hulls. The double hull basically provides for protection from collisions and groundings. And those incidents represent something like 50% of the incidents that tankers are involved with. So the double hull is providing immediately an enhanced level of protection.
OPA 90, as it's known throughout the industry, requires all tankers entering U.S. waters to be double-hulled by 2015. However, in Europe, the tanker spills of the Erika, and later the Prestige, created a new set of legislation from the International Maritime Organization.
The Prestige was an incident that occurred in November 2002 off Spain. Unfortunately, it led to a very bad pollution, very major pollution of the beaches of Galicia. It also led to a lot of new legislation. It has led to an accelerated withdrawal, forced withdrawal of single-hull tankers.
The international mandate, which has not been adopted by the United States, requires tankers to be completely double-hulled by 2010. But the tanker owners doing business in U.S. waters have more immediate concerns than the double-hull deadline. They have to make sure their current fleet of tankers can pass the stringent maritime regulations enforced by the U.S. Coast Guard.
The U.S. Coast Guard has the unique responsibility for being the maritime service that protects America's waterways, ensures safety and commerce at the same time. When the Coast Guard comes aboard a tank ship, our concerns are to make sure that the vessels don't create a pollution hazard to the area.
On a warm June day in Long Beach, California, the British Pride has just returned from the Middle East, carrying 2 million barrels of crude oil in its hull.
Morning, Captain. I'm Rick Hawkins, United States Coast Guard. This is David Nguyen and Mike Garcia. How are you doing today?
Good morning. Welcome aboard. I'm fine, thank you very much.
What we're here today to do, Captain, is conduct your annual Certificate of Compliance inspection.
If major problems are found aboard the British Pride, the ship won't be allowed to discharge its cargo, potentially costing the vessel's owner tens of thousands of dollars a day. One of the most important anti-pollution devices on board a tanker is the oily water separator. The system works by processing the oil that exudes from a tanker's machinery and collects in the lowermost part of the ship, known as the bilge. When the oil is diluted with water to acceptable levels, it can then be discharged into the ocean.
There are safety systems built into that equipment where, should the oil reach a high level, that alarms will sound and automatic systems come into play. Valves will close, so there's no accidental discharge. Thank you.
After examination of the oily water separator, the wheelhouse is tested.
We go from hard port to hard cellar. Output, how's that? That's hard port.
Emergency firefighting equipment is checked, and manual control of the ship's rudder is inspected. Upon completion, the vessel is given permission to discharge its cargo.
Based on the inspection this morning of the Pride, the ship was in very good condition. The crew, the officers, and the deck crew were very competent and very cooperative. And all the machinery that we inspected was in very good condition and operated as intended.
Monitoring the hundreds of oil tankers entering U.S. harbors is a huge responsibility for the Coast Guard. And they're about to get even busier, as the tanker industry is currently undergoing the highest level of new ship construction since post-World War II. The largest oil tanker spill on record occurred in 1979, when 2 tankers collided off Tobago Island, spilling approximately 280,000 metric tons of oil into the Caribbean Sea. Oil tankers will return on Modern Marvels. At the National Steel and Shipbuilding Company in San Diego, California, BP is building 4 new Alaskan oil tankers to meet the OPA 90 deadline of 2015. At 185,000 deadweight tons, each ship consists of 34,000 tons of steel and requires 106,000 gallons of paint. But what is unique about these ships is a redundancy system that ensures a level of safety far beyond the requirements of OPA 90.
We call it double-double. It's double hull, double engine, double propeller, double everything. And they're designed to enhance the safety of transporting oil out of Alaska waters. If the engine were to fail, the other one could operate independently and propel that ship. The same with the rudder. If you were to lock your rudder in and you couldn't move that rudder, you could actually shut down that engine and operate off of a separate propulsion system.
The rebuilding of BP's tanker fleet won't come cheap, as each Alaskan tanker will cost nearly $250 million. But BP has found at least one way to help offset the cost. Oil tankers reserve several tank compartments to store seawater. This is used to ballast the ship after cargo is discharged.
If you take a simple idea of an outer wall and an inner wall that we now call the double hull, you can use that space for ballast. When you do, you can use more of the internal tanks to carry more product, crude oil or gasoline or whatever you may be transporting. You actually get more efficient use of the space.
The Alaska Frontier will be the first of BP's new Alaskan-class oil tankers to begin service.
I name the Alaskan Frontier.
When the Alaska Frontier sails, it will be the safest tanker sailing in U.S. waters.
However, BP isn't the only company that is undergoing a massive rebuilding of its tanker fleet. New legislation has brought about the highest level of tanker construction since post-World War II.
The reason is the industry, ahead of the deadline, is beginning to build their double-hull tankers around the world. By 2010, which is still 5 years before the requirement for all double-hull, approximately 85% of the world's oil tanker fleet will be double-hull.
But in spite of the new, stricter laws and regulations, there are critics who believe there are bigger issues at hand.
Double hulling a tanker adds safety, for sure, but it's not going to fix the entire problem. It's a Band-Aid solution in the end. Oil tankers are not the problem. Oil is the problem. Our nation and most nations in the world are over-dependent on oil. We're addicted to oil.
While renewable energies are being developed, their evolution remains slow, and the world's demand for oil continues to increase. But oil is a non-renewable resource, and its supply will one day be exhausted.
Today we're talking about oil being available certainly for another handful of decades, 20, 30, 40, 50 as routinely talked about. So for the tanker owner, there is not a real concern today that the world is about to stop shipping oil. In parallel with the exploration of oil and the utilization of oil, gas is becoming a substitute in many cases for oil. It is the growth industry in terms of an energy source.
It's cleaner, it burns more efficiently, and has a huge role to play in reducing greenhouse gases and emissions around the world.
Transporting natural gas to the United States will be the job of the LNG, or liquid natural gas tanker. LNGs store the gas in liquid state by cooling it to a temperature of minus 256 degrees Fahrenheit. In addition to their more environmentally friendly cargo, LNGs are less polluting than oil tankers, using mainly natural gas for propulsion. And at 900 feet in length, with a draft of 36 feet, LNGs can enter ports that would be restricted to most large-sized oil tankers. While the current LNG fleet numbers just under 200, that number is expected to increase in the coming years.
Some reports suggest that by 2050 there will be as many LNG carriers, 450, 500, as there are very large crude carriers, oil carriers today.
Although oil tankers remain the most important energy lifeline to the world, the increase of the LNG fleet signals that its tenure of dominance is limited. Declining oil reserves combined with a global increase in energy consumption will inevitably force the proliferation of alternative fuels.
As alternatives emerge, as we start to develop other ways to get around in our cars, hopefully tankers will become obsolete. Hopefully refineries will become obsolete and we will get off of our oil addiction.
But the footprint left behind by these steel giants will endure for generations to come.
I think in the future there'll be a realization that it was indeed a marvel of the time, a necessity of the time.
It's an industry that continuously improved, that used innovative techniques to make the movement of hydrocarbons even safer, that supplied much needed energy to places that before ships were built the way they are, we couldn't get the energy to.
The oil tanker will forever be linked to the spectacular growth of the petroleum industry. It will serve as a reminder of a time when nations depended on oil from thousands of miles away to power the industrialized world.